Designing synchronous counters. There are times that you want to design a counter that cycles through a particular sequence of counts. Here's the state diagram of the synchronous counter that we'll design in this session. As you can tell by the fact that it counts in order and that its maximum count is 7, a 3-bit value, we will be designing a sequential 3-bit up counter. The state excitation table is used to figure out what logic is required for the inputs of each flip-flop. As in a state transition table, the first column is always an ordered list of all the different states in which the system can exist. We need 3 bits to represent the maximum value, therefore we need 3 flip-flops. There's one column per flip-flop, with the most significant bit on the left and the least significant bit on the right. The second column is for the next state. Here we will use a state diagram to identify the count that follows each of the present state values. The last set of columns are used to work out the logic for each of the flip-flops. Because there are 3 sets of columns, again ordered most significant to least significant. Each has 3 sections, the first for the transition from the present to next state, followed by 1 for each of the J and K inputs. The layout of the table shows you the present state, the next state, and the transition of each flip-flop in the system, color-coded here to make it easier to see the columns that work together. The first thing to be done is to populate the next state column. Remember that we're designing a sequential up counter, so a count of 0 will move to 1, 1 to 2, and so on. Now we need to look at the transitions that each flip-flop must make to get from its present state to its next state. Starting with the most significant flip-flop, we need to look at the 2 columns for Q2. In the first row, Q2 starts at 0 and holds. We show that in the transition column as 0 to 0. The transitions in the second and third row are the same. They start at 0, stay at 0, therefore we mark in a transition of 0 to 0. The next row has a transition from 0 to 1. Each column for the flip-flop gets marked in with the appropriate transitions. Now before we can complete the rest of the table, we have to take a closer look at the JK flip-flop. The truth table for the JK flip-flop reminds us that the output holds when both J and K are low, resets when J is low and K is high, sets when J is high and K is low, and toggles when both are low. Now if we think about the transition from present state 0 to next state 0, it can occur in one of 2 situations. First, as the result of a reset, and second, as the result of a hold. Similarly, the transition from 0 to 1 can occur when either a set or a toggle occurs. The transition from 1 to 0 can occur when either a reset or a toggle happens, and the transition from 1 to 1 when either a set or a hold happens. What's important in all of this is what's in common for each transition. In the first set, J has to be 0, but it doesn't really matter what K is. In the second set, J must be 1, but K can either be in the high or low state. For the third set, K must be 1. It doesn't matter whether J is a 1 or a 0. Finally, in the last set, K must be low, and J can be in either state. We'll summarize all this information into a table that we'll use to fill in the rest of the state excitation table. This transitions table shows us each of the 4 possible transitions: 0 to 0, 0 to 1, 1 to 0, and 1 to 1. We figured out for the transition from 0 to 0 it could be either a reset or a hold, and that J had to be 0. We'll mark that on the table. J is 0, and K is a don't care. For the transition from 0 to 1, which was either a set or a toggle, we determined that J had to be high, and that it didn't matter what K was. For a high to low transition, either a reset or a toggle, K had to be high, and J was a don't care. Finally, for the high to high transition, either a set or a hold, K had to be low, and it didn't matter what J was. This table gives us all the information we need to populate the rest of the excitation table. The first transition for Q2 is 0 to 0. Our transition table shows that the entries for J and K should be 0 and X. The second row is the same. We fill in the rest of the cells using the same transition table. We're now ready to figure out the logic by simplifying each of the J and K columns using K-maps. Using the values in the column for J2, we can populate a K-map. The largest group that includes all the ones is Q1, Q0. Putting the values for K2 into a K-map, we can see that the largest group that includes all the ones is the same, Q1, Q0. With the values for J1 dropped into a K-map, we can see that the largest group that includes all the ones is Q0. Putting the values for K1 into a K-map, we can see that its largest group is the same, Q0. With the values for J0 dropped into a K-map, we can see that all the cells can be included, giving us J0 equal to 1. Similarly, we'll see that K0 also simplifies to a 1. Now we're ready to complete the circuit diagram for our synchronous counter. First, we draw the required number of flip-flops and make sure that each clock input is connected to the same clock signal. Next, we add the input connections for each flip-flop. Starting with the flip-flop with the least significant bit, Q0, we determined that J and K were both to be tied high. We mark that in. Moving to the middle flip-flop, Q1, we determined that both the inputs were controlled by Q0. We mark in those connections. Finally, to the flip-flop for the most significant bit, Q2, we found that the logical card for both J and K was Q1 and Q0. Once those connections are marked in, our circuit is complete. So to summarize, when designing a synchronous counter, make sure you carefully follow these steps. First, create a state excitation table that has a column for the present and next states, plus a set of J, K, and transition columns for each flip-flop in the system. Fill in the present state column, making sure you have an ordered list of all the possible states. Use the state diagram to mark in the counts for the next states. Identify the transition for each state change for each flip-flop. Fill in the transition columns using the JK transition table. Use K-maps to determine the logic for each J and K. And finally, draw your synchronous counter.